So in other words, you're dealing with a problem that has the endpoints. You're finding the integral from 2 to 5 or from 7 to 12. Substitution works also for problems like this. And I'd like to talk about an example and show you two ways of proceeding, and then you can take your pick as to which is the easier way in a particular problem. Let's look at the integral from 0 to 2 of 3x squared times the square root of x cubed plus 1. Now, I hope you're saying to yourself, I could do this as follows. I could find the antiderivative of 3x squared times the square root of x cubed plus 1 using substitution. Let me tell you who the characters would be. U would be x cubed plus 1. That's the thing inside the radical. Du would be 3x squared dx, and I've rigged the problem so that it's right there in front of us. It doesn't take any work, not even any massaging. So this would be a fairly straightforward problem. You would find that antiderivative, and then you would plug in the endpoints, and you'd get the right answer. That would work fine. But let me show you a second way that you might prefer, and it's the following. Do the same substitution. U is x cubed plus 1, du is 3x squared dx, and now change the endpoints of the definite integral into the new variable u. In other words, change the entire problem from x's all the way over to u's. Even the endpoints will be changed now. Here we go. X starts at 0. That's the lower limit of integration. X was 0. Well, u is equal to x cubed plus 1, so u would be 0 cubed plus 1, or 1. That's the new lower limit of integration. X ends at 2, so u becomes 2 cubed plus 1, or 9. So in u land, when I change over to the u variable, my limits are going to be 1 to 9. And now let's change the integrand into u variables. The square root of x cubed plus 1 becomes the square root of u, or u to the 1/2, and the 3x squared dx becomes du. So we're left with the following problem completely in the u variable. From 1 to 9, u to the 1/2 du. It's as if we were given another problem. In a sense, you can forget the old problem. Let's solve this one. It's pretty easy. The antiderivative is u to the 3/2 divided by 3/2 between the limits of integration 1 to 9. I'll flip the fraction up, 2/3, and now I'll evaluate it first at 9. 9 to the 3/2 is the square root of 9, or 3 cubed, i.e. 27, minus 1 to the 3/2, which of course is 1. So the final answer is 2/3 times 27 minus 1, or 26 times 2 over 3, or 52 over 3. And that's the answer to the original problem as well. Now let's look a little closer at this. This is kind of an interesting observation I'm going to make here. We had two problems here. First, we had the original problem using the x variable. And that was a certain area under a curve because the function's non-negative. And then we had a new problem in the u variable. And that's another area problem. And in both cases, the area is 52 over 3, the final answer we got. So the area under the original curve, x cubed plus 1 square rooted times 3x squared, between 0 and 2, is precisely the same area as under the square root function between 1 and 9. Let me show you a couple of pictures here. On one picture, you'll see the original function on the interval from 0 to 2. And on the other diagram, you see the square root function on the interval 1 to 9. And what we've just observed is they have the same area. The integrals don't look alike, but they both calculate to be the same answer, which is the area under those curves. Great.